So today I'm going to be talking about physical replication at a SyncConf that's all about mainly logical things like CRDTs and so on. And you might be wondering why I've chosen this topic. As Jan said, I have been in databases for a very long time, and databases use physical replication to achieve some really amazing things. A couple years ago, I switched from full-time on databases to being full-time on research in offline first and local first and collaborative applications. And I've really been interested in bringing some of those things I've learned while building databases to the world of offline first. And today, I'm talking about why physical replication still matters and why you should consider it when you're building something like a sync engine. So, replication. I love the matrix. There's going to be a lot of matrix memes in this, so bear with me on that. Am I getting an echo or is it good? Good? Okay, cool. So yeah, what's replication? I mean, what replication is copying data from one place to another, and there's many ways to do this. There's many forms of replication, and we're going to be talking about sort of two main categories of replication. I find this way of thinking about replication to be very intuitive for myself, and I'm going to try to explain it to try to get us all on the same page. So we have logical replication and physical replication. As I said earlier, logical replication is sort of like a CRDT. It's like a description of change, where physical is a little bit more low level. We're talking about the exact bits and bytes that are actually being changed. So let's say we're building a sync app, and we're building like a collaborative drawing app. I'm sure that's never been done before in the world of sync. So let's just build one from scratch. And our app only has one operation. It's just really interested in mustaches. And in a logical system, we would describe the change that we want to produce. So when a client receives a change, it would receive a very logical description of that change, like essentially a description. And it would be up to the client and the sync engine to actually reconcile that change into the state. And so this is a very trivialized example of what's going on, but it's a good way to think about it. It's like this operation only encodes enough information to be able to apply the change, assuming that there's code that knows how to interpret this change. That's what makes it logical. It's sort of domain specific. But we could build the same sync app, like the same design app, using physical replication. And in this world, instead of sending this logical operation that requires interpretation, we would instead send the literal bits and bytes that have changed in the image. So you can think of this as like a binary patch, right? In this example, we send the literal mustache that we want to paint on the image, and the application actually doesn't even need to know what the data is. Right? This is a completely agnostic system. All we know is we get bytes in, we put the bytes where they need to go, and we've now replicated, we've synced the change. So as I said before, I like this sort of way of thinking about things. And we're going to use this quite a lot, these analogies that I've used throughout this talk. Okay, so at the beginning of the talk, I said we're going to be talking about physical replication and sort of where it fits in the world. And the way I structured this talk is thinking through how you might want to build the properties of physical replication that either help or hinder you when you're building something like a sync engine for a collaborative app. And I'm going to focus on these 6 categories of features that a sync app cares about. And then we're going to look at how physical replication sort of fits into each one of these. And I'm going into detail on all 6, so I won't say them here, but you can read through and get an idea of where we're going. So the first feature is storage agnostic. Now this is not, by the way, these features are not universal. Like every app has a set of trade-offs and a set of business rules and business logic that they want. But sometimes it's very, very nice to be able to take a third-party system that already exists, some storage that already exists, whether that's a file format or a database like SQLite or something else, and be able to use that existing file structure, that existing data structure with your sync system. In this case, we're using SQLite as an example, and we're basically treating it as like a bunch of pages. I'm going to say the word page a lot, so I want to be crystal clear about what I mean by that. When I say the word page, what I mean in this talk is a power of 2 size of bytes that are a subset of a file or a subset of a database. So in this case, SQLite uses pages extensively internally, and the default page size is 4 kilobytes, and they use it to represent these B-tree data structures that make up a SQLite database file. But The first property is storage agnostic, and physical replication works really well for this because physical replication doesn't care about what the data is. It simply just ensures that over time, the downstream consumer, the client, is going to see the exact bits and bytes that you sent. And so it's really powerful because you can apply physical replication to sort of any physical system. Like if you already have a data structure, it just works. So the second one is consistency. And now consistency is a very overloaded term. We hear like consistency, like eventual consistency a lot of times. We have, for example, like acid and cap theorem and all these things. There's many different forms of consistency. The consistency I'm talking about is how do you know that two nodes are looking at the same thing? With physical replication, because physical replication guarantees that they see the exact same bits and bytes over time, all you have to do is just look at those bits and bytes. If they have the same bits and bytes, they're consistent. And this is really a cool property. It's a very simple, it seems like a simple property. It's like, why am I even saying this? But when you're working in a logical system, it's really hard to guarantee that two nodes end up with the exact same bits and bytes on disk. And usually what you end up having to do is add either like hashes in your data model or do some kind of like recursive walk through your data model to be able to actually prove that two things are seeing the same thing. So physical replication, really, really good for consistency. And the third one is bulk changes. And this is a sort of another subtle thing, which is that physical replication doesn't really care about how much you're changing. It's essentially the amount of work you have to do to apply a physical patch to a file is loosely like linear in the size of the patch. And that's a really nice property. If you're working with really large data, like I worked on databases that were in the petabyte and terabyte range, you don't want to have something that's like exponential to the size of the change. You want something that you can apply very, very cheaply to the system. And physical replication can do this because it's just applying binary patches. You don't have to interpret those patches. And this is at odds with other replication solutions, which you have to actually interpret the patches as you go. Okay, but physical replication isn't perfect. There's a lot of things that it's really awkward at doing. And one of those is partial replication. The way that most physical replication systems work is essentially you have like a change log, which I'm representing as like a bunch of images of things we've like added to this picture of Neo. And we have two devices which only care about like a very small amount of the overall data. Obviously, I'm using a picture of Neo. It's a very like silly analogy, but I hope it's like understood that this device only cares about this cropped subset of the data, right? The data might be a terabyte, but we only care about 100 megabytes. But the problem is that most binary like physical replication systems send essentially the way that the change log is structured, like the write-ahead log or the wall you might have heard of, essentially forces clients to download and interpret all of the changes to be able to ensure that the data structure is consistent and correct. This makes it really hard to do partial replication because we would essentially need to send all the data to every single client. And that's not something we want in a collaborative system or like an offline first system. We want clients to be able to only get the data that they care about. Okay, the next one is conflict resolution. This one is another one that physical replication really struggles with. So let's say that two clients make two independent changes. One of them adds a purple mustache to Neo, and the other one changes Neo to like black and white. In physical replication, we would represent these two changes as essentially like, just the bytes that were changed, which means that physical replication has no way of representing this potential third outcome where the mustache is actually black and white, because the data just doesn't exist in the model. Like there's nowhere for it to fit. Physical replication doesn't have enough metadata and sort of understanding of the domain of the data to be able to apply that change and perform perhaps what the user who made the system black and white actually intended, which is I want the entire thing to be black and white, not just the portion that I happen to have seen. And this is a really powerful aspect of logical replication, and in my opinion, one of the biggest reasons why the majority of this industry, the majority of people in this room, wouldn't even consider physical replication in the first place, because it can't do this thing in the same way. And the last point I'm going to make is about permissions. Permissions is a huge problem in general. It's really hard to do permissions at scale. It's really hard to do permissions in any system. But physical replication has its own set of problems. And one of them is that physical replication doesn't know what the data represents. it can only do very coarse-grained sharding at the level of the file level or the page level. But if you want to do sharding at like a sub-page level, where essentially, for example, in this example, you might want to ensure that Neo gets access to their tasks and Agent Smith gets access to their tasks, but they don't get to see each other's tasks, right? In this world, physical replication doesn't have enough metadata to know about which portion of each page to send to each node. And permissions is a really important thing in local first, in collaborative. And so physical replication doesn't really work well for that. You have to sort of figure out a way of sharding your data to be able to work around this limitation. Okay, if anyone knows me, I'm the type of person, I like to tell people trade-offs up front. I don't want to tell anyone that's like, this thing is perfect, and just pretend that these other things don't exist. And that's what I'm doing right here. I'm saying that physical replication has some really cool properties, and really amazing database systems and like really powerful distributed systems make use of those properties to do really cool things. But when you're looking at using physical replication naively, just like straight out of the box to do something like collaborative or local first, you have some problems. Now, as we know, we're software engineers, and we like to hear things like, you can't do this. And what we instead hear is, I'm going to figure out how to do that on the weekend. And that's what I did 2 years ago. I was like, it shouldn't be that hard. Like, I could figure out how to get SQLite to just be collaborative. Like, let me just see what happens. So 2 years ago, I started working on a project called SQLSync, which is my approach, my attempt at solving conflict resolution with physical replication. Like, what does that look like? And then this last year, I've worked on a project called Graft, which is my attempt at solving partial replication over physical replication. And these are very much research projects. Like, I'm very excited about them, and I think people can definitely start using them. But they're very much experiments to see which ways we can push the system and what we can learn from it. SQLSync is the first project, as I said, conflict resolution built on top of physical replication. The insight with SQLSync that I made was that you can actually do both. Like, why don't we just do a hybrid model? Like, physical replication really sucks at conflict resolution. So instead of trying to solve that, can we get some of the advantages of physical replication by just changing the problem? And or like the goal. And so what I decided to build with SQLSync was this architecture. Essentially, the idea is that we logically stream changes up to a coordinator or a server. And the coordinator could be like a peer that is elected in a consensus group, could be a server. It doesn't necessarily have to be a centralized thing, but it's simpler to think about it like a centralized thing. We can do conflict resolution and permissions at that point because we have all the logical metadata we need to do this. But we can take advantage of the coordinator then streaming back physical pages down to clients. And we get this sort of cool outcome of this, which is that for clients who don't ever need logical replication, or when you don't need real-time collab, like there's many times where you just open up a document and you want to just quickly bootstrap the document, we can take advantage of the power of physical replication to do that really quickly. We don't need to boot up an entire sort of logical representation of the document. So that was the idea behind SQLSync. And in the interest of time, I'm going to fast forward through the explainer of SQLSync because I was optimistic about time. So really quick, basically clients throw tasks in a log. The log goes up to the coordinator. The log is logical, right? So essentially the coordinator can actually do all the conflict and write permissioning in the log. The coordinator then applies those changes directly to SQLite. These changes end up looking sort of like API calls, which is a really nice property for developers because you don't have to think about anything beyond just how do I apply changes to a SQLite database. And then the big idea of SQLSync, which other projects have also done, is basically the idea of rebasing. The client can replicate down the physical pages that have changed in the authoritative version of the database, and then we can quickly replay our local log and get rid of anything that has already been applied, and then just replay the unapplied changes. And this works pretty well. Like SQLSync works, and you can go play with it today. There's a QR code in the bottom right, but I'm not going to pause, so go fast. All right, so really quick, what have we gone over? Like we've gone over physical replication, we've gone over SQLSync, and we've talked about how SQLSync sort of solves conflict resolution and write permissions. It provides those features on top of physical replication, which is what I set out as a goal. But it still has some problems. One of them is partial replication. I didn't solve that. It's just like SQLSync just sends all the data to every single client, which is explicitly what we don't want. And read permissions. So my next project was called Graft. Graft is storage agnostic partial physical replication. It's an open source project, and it's designed to be embedded in your application. It's not a standalone system. It's not a service. It runs as a library, just like any other open source library in your app, and it supports replicating to and from directly to object store. And what Graft is just like a very vanilla serializable physical replications. Like you can think of it as like a physical replication log representing state. And as you write to that log from one or more devices, essentially we are just applying those writes directly to the state, attempting to commit it to object store. If we conflict, we come back, we replay our writes, and then we try to commit again. So it's not designed for high write concurrency, but what it is designed for is extremely high scale out read concurrency. Because we can do partial physical replication, devices only download the small fraction of data they care about. And this is a really cool property. All right, what's our timing at? 9 minutes. Oh, perfect. Okay, so the insight of Graft, the key idea that I made was that if you take like a traditional physical replication log, which is like a write-ahead log, you normally would see the changes and the log metadata in sort of the same place. We would essentially just have a log which contains all the changes. What if we just split up this? What if instead of doing that, we store the pages that have changed in the log and a little bit of sort of causal metadata, and then we store the actual data somewhere else? And then we just make it really easy for clients to go and retrieve that data and the subset of the data that they want. What does this like lead to? So what it means is that a client, so like we go back to our mobile device example, a client essentially sees like a commit log, which is very lightweight. The client can like even a very small mobile device can stay up to date with this commit log because it's in the kilobytes in size. It's super small. But from that commit log, it can essentially intersect that commit log with the client's visibility graph or visibility state. And in this case, we're just intersecting like essentially which portion of an image we care about. But if you think about a SQL query, for example, the visibility graph is essentially all the pages that we need to satisfy the SQL query. And once we've done that intersection, and there's some complexities around like, what if you don't know which pages you need, and there's index lookups and stuff like that. So you can do this iteratively. But once you've done that intersection, what you end up with is essentially very fine-grained lookup into the actual data. And this is partial replication. Essentially, it allows a client to go and download those tiny bits of those pieces of data and apply it directly to the state and never see anything else. All right, so what we're going to do is attempt to do a real demo. This is on Wi-Fi. This is connected to S3, and if this fails, I will walk off the stage. So what we're going to do is we're going to run Graft. And so what I've done is I've wrapped SQLite, and this is vanilla SQLite on my computer, just like what ships with Mac. And all we've done is we've pointed SQLite at a shared object, which represents my virtual file system. And that virtual file system intercepts all of the reads and writes to the underlying database file. And instead of reading and writing to the database file, instead it reads and writes to Graft. And then Graft does real-time sync up and down to S3, Tigris. Now, what I've done is last Friday I had this crazy idea. I was like, what if I make it like Git? And it turns out it's really nice because it allows me to demo this a little bit more slowly instead of just having like everything be instant. So we're going to do this as a series of steps. The first thing we're going to do is we're going to clone. By the way, is the text big enough? Okay, cool. So we're going to clone a Graft. And what that means is not much yet. But what we can do is run Graft pull. And this is the first point where we're querying Tigris. So we've just reached out to Tigris. And what we've done is we've essentially just downloaded the commit log of this Graft. And so we now have all the metadata that we need to know exactly where to go and get the individual pages that we want. And then what we're going to do is we're going to run Graft audit. And we're going to see that we've cached 0 out of 177,000 pages. Great. So far, so good. We'll run Graft info, and it will tell us that this volume is 700 megabytes in size. And it would be insane for me to run a demo where I ran a this is going to be crazy, where I ran a demo of this query, which happens to be joining against 3 different tables on a 700 megabyte database. One of those tables is the majority. It's like 90% of this database. And so if all goes well, if this doesn't time out or take forever, what's happening is essentially we're doing a full lookup, figuring out which pages we need, and this is completely unchanged SQLite. And the real interesting thing here is if I go back and run Graft audit, we'll see that we've only downloaded 0.77% of the database. So this is Graft, and I'm going to attempt to do one more part of the demo here. I wanted to do, let's see, I do have enough time, so we can maybe play around with some stuff. But what we're going to do is do another thing, which is doing a consistency check. And while that is running, what it's currently doing, this is a bad idea, I shouldn't have done that. It is currently downloading the entire data set. We don't want that because I wanted to show, oh no, it worked, okay, cool. So now if we run audit, okay, yeah, so that's cool. So what we just did, this is crazy and cool, is that on Wi-Fi at a conference during a demo, we just downloaded 700 or 800 megabytes, which is nuts. And then what it did, which is interesting, is that it found the 800 megabytes which represent the most recent consistent snapshot of that database. And so we've not just downloaded the full data set, but we downloaded like the most recent snapshot just from looking at the metadata. And then what we just did is we ran like a checksum hash over that entire data set, which was instant, which is just the power of the fact that we're using physical replication. All right, 3 minutes, that is, I think, good enough for a demo, but the basic idea is that Graft works. You can use it today. I was going to show some other things like, like writing. So like we have the ability to write to the database, and we can like Graft push, which is like Git. We just uploaded data to S3, and we could go and pull, and we could do multi-writer and all that fun stuff. It works basically like Git, except if Git was a SQLite database. All right, now this is, yeah, cool. So going back to the talk, so we've just looked at Graft, we've just looked at what it can do, and it's one thing it can do is partial replication. It doesn't try to solve the other things. I'm interested in solving, like building composable tools that all of you can use to build really amazing things. And the question really that I have is like, what's next, right? What do I work on next? And I have a lot of ideas. One of the ideas is integrating SQLSync and Graft, right? Graft actually was like originally inspired by my experiments with SQLSync, and it's a very natural alignment. It allows SQLSync to be sort of end-to-end sync engine with all of these features. But the other thing that I'm interested in is read permissions, and I'm really interested to see whether or not there's ways I can approach solving that problem, because that's still an open problem in the world of physical replication. So I'll leave you with this slide, which I think is a starting point for the types of questions you might want to ask when you're thinking about using physical replication in your app or your project or your real-time sync system. The first one is, if you have a lot of data or you're doing big bulk state change, physical replication is just very efficient. It's a very lightweight protocol. You can do very large patches of state, and the size of the patch or the cost of the patch is linear in terms of how much state's being changed. You don't have to do any interpretation and stuff like that. The next one is bit-for-bit consistency guarantees. If you need to be able to do this, it's, I think, the only really reasonable way to do it. If you do bit-for-bit consistency in the logical world, you end up in the world of like deterministic software. You have to make sure that as your changes are applied, they're bit-for-bit deterministic to the actual state. And in real-time concurrent systems, especially like big databases, guaranteeing determinism when you also have things like async garbage collection and compaction and like data cleanup and all this stuff is borderline impossible, which is why databases often use physical replication. A third one is independence from storage engine. If you want to just throw this on SQLite without touching SQLite, this is a system to do that. There's also fast bootstrap, so you can do a very fast forward to the latest version of state without having to replay the entire log, because you can do this page selection algorithm. And finally, high fanout replication. If you're streaming reads to a very, very large number of places, physical replication is a great way to do that. And that's all I have. I have 9 seconds left. Thank you so much, and have a great day.